All right. Hello, everyone. Also from my side, it's nice to be here. I would have liked to meet all of you in person. It's one of the highlights of the year. The Flink Forward conferences, the meeting face to face all the folks that you otherwise only see discussing on mailing lists and Jira issues on Twitter or so. But it is what it is these days. So I actually hope that you enjoy this setup as well. Big thanks to Holger and everyone who has actually tried to put a lot of work into making this a good experience. I'm here today to talk about, the title of the presentation is Flink Ahead, What Comes After Unified Batch and Streaming. It's been kind of customary though to before diving into the main topic to look a little bit at what was going on in the community in general over the last year. So the mandatory recap of the last 12 months in Flink. I've done this, I think, in almost every keynote that I've given at Flink Forward conferences, so definitely want to do this year again. And there's lots of things to share that were pretty exciting that we're very proud of. The first thing I would like to start with and share is actually an extremely impressive achievement of the community. That is just how active and vibrant it is. And the Apache Software Foundation releases an annual report every year on what is going on in all these different projects. There are hundreds of projects in the Software Foundation. Flink is one of them, and they often have like a ranking of which projects are most active on mailing lists, on code development, and so on. And it was just incredible how Flink showed up in this last report. The most active user list in the entire foundation. The development mailing list is number 2 across all projects. The repository, just by commit activity, by activity of developers adding code, number 2 in the entire foundation. The visits to the repository, so users browsing code, number 2 in the entire software foundation. That's just mind-blowing because it is a foundation of a lot of very big projects, and Flink being so active and so vibrant in there is, it's just a testament to everybody who is participating to their dedication to making this a great experience for developers and for users. So a very big thank you to all of you who actually participate and make this possible. This is really, I think, an outstanding example of a really, really great open source community. Here are some charts of how the activity developed over the last years. GitHub stars on the left-hand side. On the right-hand side, you see how the mailing lists are developing. You can see the user mailing list oscillating around 750 discussions per month, which is a lot. The dev mailing list, oscillating a little bit around release cycles and so on. There's a second mailing list in Chinese language that is taking off, growing very rapidly. All in all, very high numbers of discussion activity all around. What's also very impressive is if we actually take a look at what happened over the last releases, how many contributors are active and working on every release. So the releases are getting bigger by number of commits, by numbers of issues addressed in there, but also by number of people participating. It's the third bar, the one that is a little lower than the others. And it's worth pointing out that it's not cumulative contributors to Flink in total, but it's really the distinct number of contributors for each and every release. So you can see that this is actually going up. And the Flink 111 release, the latest we had almost 270 individual people contributing to it, to just Flink 111, not counting the ones that contributed to Flink 110 and before. So that's really impressive as well. And again, big thank you to everybody who is working on this, who is actually helping outside contributors to contribute, mentoring them, helping review and merge issues. But not only community activity has been extremely impressive, I think, in the last 12 months, there's also been a really big number of very impressive features that have been developed by the community and added to Flink all in all. Here's some highlights. It's actually impossible to fit all of this on a slide and to talk about all of this in detail. But I hope these selected examples just show you also the breadth of topics that are being worked on and discussed and improved over time, starting from SQL to memory management, deployment modes, reworking checkpointing with underlying checkpoints, adding a whole new subproject like stateful functions, adding a completely new language like Python, UDF support in the table API, and now coming up actually a full Python version of the data stream API. A lot of very impressive stuff. One thing I would like to dig into a little more, because it's a very nice development that we actually haven't shared before, is the progression of performance on the SQL side, just as an example of what has also been happening there over the last releases. So this is a Flink to Flink comparison to keep it fair and unbiased. We're looking at how the performance evolved over individual versions. And we use as a comparison baseline the TPCDS benchmark. It's a standardized decision-making data warehousing benchmark on a 10 terabyte scale with a cluster of 20 machines. And it's a pretty big set of queries, and the time you see there is what Flink takes in order to crunch through all of these queries. And from Flink 1.9 to Flink 1.10, there's a lot of work on the sources, particularly the fully integrating vectorized processing from the readers, reading ORC Parquet into the runtime, exploiting the vectorized columnar processing more efficiently. So that actually gave a pretty big speed up. The 2.x you see there it's not a single query that was sped up by 2.x, so it's not like a very select thing that only applies in a couple of cases. It's like the overall speed up across all tens of queries that are in the TPCDS benchmark as a whole. So it covers a pretty broad set of use cases. Around between Flink 1.10 and Flink 1.11, didn't invest so much work in performance, but there is a lot of work invested into the ecosystem of SQL. So support for changelog, change data capture, better catalog support, streaming data ingestion into Hive. We reworked the type system, type inference, and so on. Performance stayed pretty much stable. For the next version, for Flink 1.12, there's again a 1.4 speed up, which is in this case attributed to improvements in the scheduler and better fusing of operators, like chaining of operators, if you're familiar with the Flink terms here. So all in all, the last 12 months gave us 3.x speed up for a very broad set of queries. That's pretty nice, given that it's just one of the things that happened in the community, and 3.5 that's dividing your cluster by 3 in order to get the same results. It's a pretty nice outcome. So this is all on the batch processing side. Flink's bread and butter is actually stream processing. What can we say about performance on the stream processing side? We cannot say quite as much yet because there's not a standardized benchmark for stream processing as there is for batch processing. And one thing that the community has recently picked up is it's actually trying to use the NextMark benchmark, establish a baseline, and actually track the improvements on the streaming SQL performance from here on. The NextMark benchmark isn't quite as well known. It's from a research project from Portland State University. It's actually been picked up by the Apache Beam community. That's where we really discovered it from. So a lot of the credit of developing this goes to the Apache Beam community here. And below you can see an initial plot of the performance, the throughput per core that Flink gets across different queries of this benchmark. We don't actually have numbers yet on how this develops, but this is the baseline that we want to compare to in future versions and see how we can improve this. So maybe by Flink Forward next year we can show a similar chart as we did for the batch processing side, for the stream processing side here as well. Yeah, I did just want to say a big thank you to everybody that has contributed to this. I always have the privilege to present this work when we're opening the Flink Forward conference, but it really is the work of so many people that are active in this community that actually do this work, that come up with these great ideas and actually make them happen. So really this actually goes out to all of you who have worked on this. Very big thank you for all this amazing work you've put into this project. All right, let's actually dive into the main topic of this talk, and the topic is on batch and streaming unification. It was a pretty hard choice to pick a topic for to talk about, to present. Like, as I showed on the slide before, there's a lot of things going on in the Flink community. So picking one topic is actually not easy. When I submitted, or when we announced this, when I wrote the abstract for this talk, for this keynote, I actually called it like what comes after unified batch and stream processing. And then a few weeks ago, I actually tried a variant of this talk about unified batch and stream processing at with a different audience, and it turned out it's actually pretty hard to come to a conclusion what unified batch and stream processing is. What really, what actually is part of it, what is not part of it. Does this or that actually count as unified or not? And so that kind of made it hard to figure out, to say like, what comes beyond it if there isn't really any consensus what unified batch and stream processing really means in the detail. So how I would like to talk about this actually today is by showing what is actually Flink doing, like the levels of unification it's adding here. What does actually each level give us, give the user, and where can we take this? Like, what interesting use cases can we make possible? Maybe taking a step back just for a second and recap, why do we actually care about this? Batch streaming unification, this has been floating around, this term. A lot of you probably heard it before. Why do we actually care about this? There's some maybe more, some less obvious reasons. I would say the ones that get cited the most are definitely reusing code and logic across use cases, across real-time data processing use cases and analysis of historic data, making sure that semantics stay consistent, because that's really hard to guarantee if you use completely different abstractions and APIs. Just using operating one system instead of more systems can be a use case, or can be a reason to try and go for this. The other part that's coming up more and more is actually applications that sort of mix historic and real-time data, or that do use cases like bootstrapping, where you start out with a lot of historic data and you go through this and then actually switch over to the real-time data as you've caught up. So what's actually important in a system for unified batch and stream processing? And the start is the unified APIs, definitely. That's, I think, where we need to start with. And in the simplest case, you have a unified API that allows you to write an analysis program once, and it can be transformed into a batch data flow, into a streaming data flow, being executed on different systems. That idea has been around for a while. I would dare to say you can go back as far as the days when Storm was very fresh, and Twitter had this project called Hummingbird, where you wrote a program once and you could execute it either on MapReduce or on Storm. More recently, I think Beam has definitely been a project that has pushed this unified API idea, and then depending on how you run it, on in which runners, it compiles to different data flows for batch and for streaming. On the Flink side, maybe the best example to really illustrate what this unified API gives you is actually looking at SQL. SQL is a great example of a unified API here in Flink. And let me just quickly recap the beauty and simplicity of SQL as a unified API here. So SQL is a query language defined to read tables and produce resulting tables. Let's assume we have a table that is populated as the result of, let's say, page views by users. We run a query over static table, get a static result. But we could also do the other way around and say, we start the query first, run it, as an incremental streaming variant of the query, and then, as rows come in, we compute the changes that should be made to the result to actually reflect that. So as the first row comes in, result gets changed next row. The third row actually doesn't add a row to the result, but it updates a previous one. The fourth one again updates the result. And the interesting thing is the final outcome is exactly the same. Just in one case it's computed as one whole unit. In the other case it's actually computed as a number of you can think upsert commands. But all in all, it's really the same, and you don't really have to. Yeah, you can use the exact same query, just run it in different contexts. You get the same result, just computed in one unit on historic data or on a static data snapshot. In the other case, incrementally overchanging data. One thing that's probably important to point out here is that, at least in Flink, underneath the hood, you do actually get different query plans when you run this query. Let's look at this query. It's a windowed group by aggregation query. If you run this in a batch way, what you would actually get is you'd get a group by, a batch hashed group by operation. If you run this in a streaming way, you would actually instantiate a window operator internally, the RocksDB state backend, depending on your configuration, but in the common case, with watermark triggers and everything. So it really might do something, the computation might be quite different depending on if you run it in the batch and in the streaming case. How does it actually run then? How does it actually get distributed and scheduled? That's the next level up from there that the Flink community is adding. And here's some quite interesting changes that have come up in the Flink 1.12 version. So the whole scheduling system is actually a pretty cool blend of batch and streaming scheduling in the current version. So we have a unified control and data plane, and the different queries pretty much just instantiate slightly different operators. And the core change that Flink introduces in version 1.12 is this concept of pipeline region-based scheduling. So maybe you can describe it in a nutshell as it's batching over streaming subgraphs. Let's actually look at an example here. So if we take the data flow from the previous query, and we want to execute that as streaming SQL, then we'd basically say, okay, this needs to be pipelined all the way through in order to do the low latency streaming execution. And the scheduler will treat this basically as one entire pipelined region. There's the anti-affinity between different subtasks of the same operator, so we'll, in this case, also need two slots to run it. But if we say we want to do the same thing for a batch query, we can give the batch query the liberty to actually say, I'm giving up some of the pipelining. I'm actually placing something called blocking exchanges, pipeline breakers in here. Which tells the scheduler that this actually decomposes into multiple pipeline regions. And in this case, what the scheduler will do, it will actually schedule each of them almost like as an independent batch task. So within each pipeline region, you'll actually get streaming computation, but then you get batching across the different regions, with all the expected behavior of batch processing. You can run all these regions one after another. You can run it on much fewer resources, much fewer slots than you would otherwise need in order to run a streaming computation where everything is needed at the same time. Now, one important thing here that's actually pretty cool is that this whole thing it's completely orthogonal to whether the query is actually a batch query or a streaming query. It's actually completely fine to run a batch SQL query on a completely pipelined data and control plane. So you can run the batch query without doing any batch shuffle or so, if you wish. And there's actually something pretty cool about this. There's a lot of systems that actually have this as the default mode, if you think about it. I think Presto is pretty much pipelining, streaming everything. If you remember Impala, one of the big things it had over Hive, for example, was also data was just being streamed instead of exchanged by blocking exchanges. And then the reason is this can actually often give you quite a performance edge, especially if you're in clusters that are constrained by IOPS on the local disks or so. So having this ability to really make this orthogonal to the actual execution is pretty cool. And the example I used before is pretty simplified. And what the scheduler internally really can do is it can actually combine these things in a pretty flexible and arbitrary fashion. So you can almost define any edge to be either pipelined or blocking and so on, it will be able to handle it for you, making it a combination of batch and streaming execution. And this also actually this also covers fault tolerance. So a pipeline region is basically the unit of failover for the system. So let's say we're doing a streaming execution, everything is one pipeline region. If one task here fails, what it basically means is we have to reset the entire pipeline region to the latest point, which is, if you're doing streaming execution with checkpoints, it's the latest checkpoint. If you're doing batch execution and you're not doing checkpoints, or you're running a batch query without checkpoints, then it basically means you're redoing the entire query. In the case where we were placing some blocking data exchanges, what actually happens is that Flink will initially just try to fail over the pipeline region, and then it will perform backtracking to other pipeline regions. So it basically does a streaming recovery inside each region, and then basically the classical batch lineage-based backtracking across pipeline regions. So the whole system's really, if you wish, like a mix of batch and stream scheduling in the core. So having this, what is the next step? What is interesting to do beyond that, or how can we improve use cases even more? One thing that's important to maybe point out here is what I described before at the example of SQL queries. The same thing actually also holds for data stream programs, starting with Flink 112. So if you have a data stream program that you've written, maybe to continuously process data from Kafka, and now you say, I want to use the same program on a set of files to process, then you've basically turned it into a bounded program, and you will be able to select this batch scheduling and failover behavior. So breaking data exchanges and being able to do more fine-grained failover of individual tasks, so you don't have to run checkpointing all the time. So the next level that we're talking about here, what we're trying to apply to the data stream API, is actually going a step beyond that. It's actually saying we really want to be able to unify the operators, being able to run them across batch and streaming. And why is that? Why is that actually a good thing? Why is that not a purely academic thing? Like what benefits can that give us? Here's an example of what actually happens if you try to run a data stream program on bounded input. Let's say the program you wrote for processing data in Kafka, you're running it over some data in S3 now, and you've selected, or you've kind of tweaked the system to use blocking data exchanges and batch scheduling and recovery. That is the first milestone that we implemented towards adding this feature in Flink 112. And then we looked at the throughput, and the throughput is actually, it's not great. So if we compare this with the throughput we would like to have from running this program over bounded data, let's say we use the dataset API as a benchmark here, we get actually a throughput that's a lot slower, like almost 10 times slower if we run this, at least with a RocksDB state backend, because we do want to support processing of datasets larger than main memory. Why is that? One thing maybe to mention before diving into the execution is, why does SQL not have that problem? Why does the data stream API have that problem? So the nice part is that SQL is declarative, and you have this optimizer, and you can do exactly the thing we showed on this earlier slides. You can generate a different execution plan for batch and for streaming. Now, for the data stream API, it's not quite that simple. The code is very imperative, right? There's a sample of the code here on the slide that it's a co-process function. It uses timers, it uses state, so it's extremely imperative in what it does. So just trying to route different execution plan right and left, depending on batch and streaming executions, it's not quite possible here. So we do actually have to execute that imperative code in the batch execution. What happens if we do this naively? If we just say we use the batch style scheduling and fault tolerance, but not actually adjust anything in the operators, then what will happen is the following. Here's an example of a set of events. They're grouped by user, and we're just streaming them through the system, processing them, and each one of them will actually do a lookup and a modification in RocksDB as we go through. And And it's it's an index structure that's optimized exactly for that, like for individual lookups, individual modifications, and being able to spill to disk. Worst case, for every event, we actually get a disk access, which results in pretty tough performance. But we do have a few things that we can exploit here, because we are actually on, when we're doing batch execution, we know we're on bounded input. We know we're not dealing with low latency results here. So one optimization that we can do is we can actually take the entire input, let's ingest it into a sorter, like in the same way as the dataset API does it. We sort it by key and event time. And then we use ourselves a very special state backend that just has a single key. And we just basically stream the sorted data through by user and time through this single key state backend. So first through this user, compute the windows for the next user and for the next one. The advantage is we never actually have to do any real lookups in a hash map, in RocksDB and so on. We basically have the only expensive operation we have to do is a bulk sort, which you can optimize fairly heavily. So the result of actually applying this trick is pretty massive. So the performance is almost on par with the dataset API and a whole league before what the RocksDB state backend gives you. And then the interesting thing is we actually kept the operator pretty much as it is, right? We just put a sort before it, and we gave it a slightly modified state backend. So we kind of exchanged this in the background. Otherwise, all the streaming operators that do exactly what they used to do. To be fair, I stayed vague on a lot of details here, like especially what do we actually do with timers, with watermarks, and so on. If you're interested to learn a bit more about this, there's a talk later today by Alyosha who actually goes into this feature in a lot more detail, and how it's developing, how it's going to come out in Flink 112. There's also a flip in which this is discussed if you're interested in learning some more details. So having actually this stack of unified operators is a pretty neat thing, right? It allows us to actually do optimized batch execution of imperative data stream programs. There's even a bit more that we can do, and the caveat I have to mention here is this is not part of Flink 112 yet. This is really what we're trying to investigate as future improvements to this whole unification stack. And this one is actually a really interesting approach, I think, to solve this problem of mixed data. What do you do with use cases that have some data in a more batch style storage like S3, some data in a real-time low latency event streaming system like Kafka, Pulsar, Pravega. We've actually seen this set up quite a lot of times, right? There's the news data is in Kafka, and eventually there's a job that also migrates that, let's say, from Kafka to S3, usually normalizes it, compresses it, puts it in something like Parquet, so it's fast, efficiently accessible also for the batch applications. And let's say now you do actually want to run some processing over all these together, and there's been some very interesting presentations in previous Flink Forward about how do you actually stitch together these two, like building a magic source that starts reading from S3 and then goes into Kafka. But these often struggle with a few things, like how do you actually deal with this massive amount of data in the backlog, in the processing? How do you keep actually checkpoints efficient? How do you keep your state under control so you don't completely overwhelm RocksDB? Another, I think, very interesting way to approach this is to say, actually, what we really want to do is we want to do batch processing first and then just switch batch processing over into stream processing. And that's I think, where this whole operator unification actually gives us a really cool path. So what we can, in theory, do is we can run, let's say, batch execution over the data in S3. We do track our watermarks. We don't have to emit them in a fine-grained manner, but at least we track, where the watermark would be once this batch job is over. And then we apply exactly this optimization that we had before. We sort the data and then we process it in this batch single key state backend way. And when we hit the end of each key, what we take is we take the data that is left in the state backend that is not, it's not complete windows, it's not emitted in the result, and we actually write it into a save point. And that's actually that's a very good match, because save points are actually just like sorted structures of key value pairs, grouped by keys and key groups. So this is actually a pretty natural match. Then we go through the next one. No actually in-flight state here. The next key has some in-flight state, some non-fired windows there. So we finished the batch job. We've emitted some complete results. Let's say those are the green-colored windows here. And we have some in-flight results, some windows that haven't yet fired. And the batch job is done, and we start a streaming job from that save point. So we basically load this and start processing the remaining real-time data. And the save point actually helps us to perfectly get all the in-flight data together. And both of these things together, the batch job and the streaming job, they really cover this spectrum completely, and the save point kind of fuses them absolutely accurately, correctly. So that's some really interesting stuff I think we can do with this unified execution of batch and streaming by reusing the same operators and so on, the part that we're going in the data stream API. So for Flink, we're not getting this in the 1.12 release or so, but I think this is a very, very interesting direction to investigate further to really help solve this batch streaming unification problem. So yeah, I think there's no such thing as this is batch streaming unification or so, but there are many layers to it. And with each layer you add to the whole thing, you're actually making more use cases possible, or you're making operations easier. You're getting support for different types of APIs, you're getting better performance and so on. There's one thing I would like to quickly touch upon, it's a bit different. It's a bit orthogonal to all these issues here. So, a unified system, what does that actually mean for the operations side? So far, we've talked about APIs and execution and performance, but let's say for deployment, monitoring, and so on. And we're thinking quite a bit about this. So, unified batch streaming from the operations side, what does that even mean? Is that even a thing? Aren't the requirements for latency critical online systems like stream processor very different from a batch processor, except maybe for the fact that some of the general health metrics for the system can be shared? And what we think we can definitely do is we can build a system that does feel natural in the respective infrastructure that is used for both of these types of use cases, for batch processing and stream processing use cases. How you deploy things, how you scale things. And maybe, I'm not sure how well known of a feature this is in Flink, but Flink has this interesting dual nature of being able to think in applications and in sessions. I think this actually is a good match for these kind of questions here. So the way Flink started was, we can call it the the Hadoop-inspired mindset or so, but it started with this notion of clusters and sessions. It means you start a set of processes. You start your task managers. You start a master process that runs a resource manager and a dispatcher. And these are first of all just running resources on standby. And then if you want to run something, the application actually creates a data flow graph that it sends to the dispatcher. The dispatcher it spawns the job manager, and the job manager assigns some work to the task managers. There's all this dynamic distribution of libraries and artifacts in their class loading and so on. So it gives you some very interesting properties. So you can get very fast response time to short running jobs. You can get very fine-grained resource sharing if you have a lot of let's say SQL queries that you want to run in a shared environment. So it's kind of an interesting mode to run, but it's really, I would say, more a match for the batch processing side of things. Over time, we've actually developed a second mode, that is the application mode. And I think this is something that's over time becoming kind of like the default mode for stream processing applications to think in, because I think this has really a great match for how you develop and deploy applications. We do not have this two-step starting resources and submitting a job in there, but it feels very natural to just like create a Docker image and then deploy it, start all these containers, and they'll just keep running. In this application mode, the application actually runs as part of the cluster. It's not outside and submits its work into the cluster, but the application is actually the thing that bootstraps the cluster. So we do see that the application code runs, it spawns internally a job manager, and this job manager then it distributes pieces of work to the task managers, which typically have all the libraries already available in their class paths, being part of the Docker images or so. And this is, from all that we've heard from users, it's like a much more natural match for how you deploy streaming applications. And Flink 112, if everything goes well, actually adds another really nice property to that, namely out-of-the-box support for high availability and service discovery on Kubernetes without any additional dependencies. So previously, you needed Zookeeper for that. And in the newer version, it's just going to seamlessly work out of the box. All right. So with this, I'd like to come to the end of the talk. Yeah, I'm very excited about all the stuff that we're doing there in the Flink community. Like I said, it was really hard to pick a topic. I picked this idea of like the progressive development of unified batch and streaming that we're doing there, and I hope I could give you a bit of a glimpse of what is happening there, what things are made possible, what we have in our minds there is to look in the next steps. And yeah, with that, I actually want to conclude and say thank you very much, and I hope you enjoy this conference, and looking forward to all the other exciting talks. Thank you very much.